So the topic of discussion today will be dispersion in single mode fibers. So we had discussed dispersion briefly a while ago when we were discussing intermodal dispersion, right? Basically, the broadening of pulses, right, due to different modes traveling at different velocities through the fiber, right, and arriving at the receiver at different times, right? So this intermodal dispersion, right, is basically, as we had discussed, so the group velocity depends on the mode, right? So for example, it depends on the LNM indices of the which LPLM mode it is, right? And different modes have different group velocities. So if you, for example, have a multi-mode fiber, you launch some optical power at the input, that power gets distributed among the different modes, and they all travel at different speeds and arrive at different times, right? At least the broadening, and we had looked at that in some detail in step index fibers and graded index fibers and calculated the broadening, etc. Right? Now, if you go to single mode fibers, right, one primary reason for going to single mode fiber is to eliminate this intermodal dispersion, right? Because now you have only one mode. So you would think that there should be no reason for dispersion to occur or pulses to broaden, right? So by dispersion, again, recall we mean temporal broadening of optical pulses, right? But so we'll see that even in single mode fibers, there is some dispersion, which is known as intramodal, because now there is only one mode. And this occurs because now the group velocity depends on frequency or wavelength. Okay. So even though you have only one mode, typically when we send optical pulses, right, you know from Fourier transform relations that any finite extent pulse in time will have some frequency content, right, given by the Fourier transform. So, so you'll have a collection of frequencies traveling in the fiber, right, and we'll see that these different frequencies will have different group velocities, which again means that at the receiver, not all the frequency components will arrive together, and that would lead to broadening. So, of course, this will be much smaller effect than the intermodal dispersion, right? The different modes traveling at different velocities, that's a much bigger effect. So, of course, we still gain a lot by going to single mode fibers, but we haven't eliminated the problem completely. Okay, so we'll see about this in more detail. And so that's why it's called chromatic dispersion, because it's fundamentally arising from like a frequency or wavelength dependence of the group velocity. Now this is further categorized into two: material dispersion and waveguide dispersion. Okay, so material dispersion is basically the refractive index. So in a fiber, we have, let's say, the core and cladding refractive indices. These would be actually a function of frequency or wavelength. Right? So given any material, the refractive index is not a constant, and if you change the wavelength, the refractive index changes. So that's true for any material and also true for glass, of which fibers are made. So you can see that, so when you solve for the modes, right, the N effective, of course, that we got for, let's say, the fundamental LP01 mode depends on N1 and N2, right? So if N1 and N2 change with wavelengths, then that n effective or the propagation constant beta for the mode will change, right? And consequently, you can think that the group velocity is the derivative of the propagation constant with respect to frequency. That would also change. So that's material. And then waveguide dispersion is that so even if n1 and 2 are constant, so independent of wavelength, n effective that we solve for, right, actually depends on the frequency of wave, right? So again, recall. So when we solved for these LP modes, we plotted these BV diagrams, right? So for the fundamental LP 01 mode, right, it starts from 0, looks something like that, right? So so this was solved assuming constant n1 and n2, right? We just assumed some n1 and n2 are some constant numbers, right? And so V, is inversely proportional to wavelength, right? So given some fiber with a core size and core and cladding indices, if we change the wavelength, we are changing the V number, and you can see that changes the propagation constant, right? So V was something related to the propagation constant, right? And so as you change wavelength or frequency, you are changing the propagation constant, and the group velocity is basically the derivative of, right, d beta by d omega or something. So you can imagine it's something like it's related to the slope of this curve, and the slope of this curve is of course changing, right? So as I change wavelength, the slope of this curve is changing. So that's what we mean by right. So even if n1 and n2 are constant, the n effective that we get is frequency dependent, which means the group velocity is also frequency dependent, right? So even if we so that's why it's treated as a separate effect, right? Even if we had no material dispersion, we still have this contribution to dispersion, right? So in general, we'll see we'll have both of these components, and the total dispersion will be a sum of these. Right. So why again? So why is this frequency or wavelength dependence? Where is this coming from, right? So fundamentally, again, the effect is what we are seeing is, so we are sending some optical pulses at the input, right? Sending it to some length of fiber, right? So some, let's say, some length L, which is power versus time, let's say, right? So since this is some temporal profile P of t, right? So if you take, so for example, this pulse, so the intensity of the power will look like that, right? So let's say, for example, in communication systems, bit 1 is sent as some high power, bit 0 is sent as low power. If you look at the electric field, right? That looks something like this for the pulse. Okay, so there will be some carrier frequency which is given by, so this oscillation inside here is going as some e to the I omega t, right? Where omega is related to the wavelength, right? Of whatever, so let's some laser source we are using, right? And then this envelope is what we are sort of the data we are putting onto the optical wave, right? So let's say this has some extent, some t naught, right? So for example, if you want to go to higher data rates for communication, you want these pulses to be shorter and shorter, right? Because for higher data rates, you want more pulses per second. Right? So typically in modern day communication systems, these pulse widths here are typically, let's say, tens of picoseconds. Okay? Bit rates are like tens of gigahertz. Right, so now, so basically this profile, so there is some envelope A of t, which is given by this, right, times some carrier frequency here, okay. So maybe let me call it this omega naught, which is so sort of the center frequency, okay. And then so this A of t, so that's the envelope, and along with this you could also have some time varying phase, right? So these are some phase fluctuations, basically which are capturing. So if your source is not totally coherent, your wave will not be like the carrier wave won't look a nice sine wave like this, right? There'll be periodic jumps, phase jumps. So basically, with the phase jumps, so it looks something like. Okay, so the carrier doesn't look like a smooth sine wave anymore, and the more phase fluctuations you have here, the more sort of random this looks. Okay, so for a completely coherent core source, the pulse will have a smooth like carrier wave like this. For an incoherent core source, right? So for example, for a laser or something like a single frequency laser, it will look something like this. But for example, like if you have LEDs or some incoherent sources, then the inside the envelope, the carrier wave will look sort of random. Okay, which is captured by this phase fluctuation. Okay, and the power is basically sort of proportional to mod square of this. So that just depends on the envelope. So mod A square. Right, so now if you have such a temporal profile, right? So for example, one popular or this pulse shape can be modeled in different ways, but one popular way is to just take it as a Gaussian, right? So now what you can do is, so you have some temporal waveform. Again, from your basics of Fourier transforms, I can find the spectrum by taking a Fourier transform here. Right, so this spectrum E of omega will have some, so first of all it will be centered at this omega naught, okay, because that's sort of the carrier frequency here, and then it will have some spectral width, okay. So one important thing to note is, in general, this E of omega will be a complex number, which means that for each frequency, there's an amplitude and there's also a phase. Okay. So typically, like you plot the mod of this, or like the mod square, which is known as the power spectral density. Right. Basically, how the power is distributed across different frequencies. Okay. Anyway, so the spectrum will have some extent, again, which depends on these phase fluctuations. Okay. So we can plot either the spectrum in frequency, so either omega, or you could do it in nu, right? So you have to just keep track of units. So omega is recall in radian per second, or sometimes just per second. Nu is typically denoted in hertz, right? So if you divide by 2 pi, you can plot this in as function of nu, which is sort of the absolute frequency. Omega is the angular frequency, right? Or you can also plot this in wavelength units. Right? So now in wavelength units, it will be centered at some lambda naught, which is 2 pi c by omega naught. And in wavelength space also, it will have some bandwidth. And you can relate just from the relation of this relation, right? You can relate. So, for example, you can see that delta lambda will be, right? So, if delta nu is the bandwidth in hertz, delta lambda will be the, let's say, the bandwidth in some wavelength units, for example, nanometers, right? You can, the proportionality factor will depend on the center wavelength, right? So, you just differentiate this. So you can see that the wavelength bandwidth actually depends on your center wavelength of frequency, right? So for a given frequency bandwidth, the wavelength bandwidth will depend on which wavelength you're operating. So, for example, 100 gigahertz at 1 micron is not the same as 100 gigahertz at 1.5 micron in terms of nanometer band. Right. So depending on again these phase fluctuations, right? The width of the spectrum is different. So for incoherent sources, like LEDs, also these devices called laser diodes, which are sort of, you can think of them as multi-mode lasers. Okay. Of course, your light bulbs, any thermal sources are incoherent sources, but they are not really used in fiber optics. So, for incoherent sources, basically this width of the spectrum will be much bigger than. So recall we've taken some envelope here, which has a pulse width T0, tau naught, right? So, I mean, you know from your Fourier transforms that if you take some signal which has an extent from delta t in time, then in frequency the extent is 1 over delta t, right? But that's true only for signals which are real, right? Which don't have any phase here, temporal phase. Okay, so if you just took this envelope here, took the Fourier transform, then you'll get a frequency extent which is 1 over. But here we're looking at some complex signal here, right? So actually, the we're looking at is this, right? Not the envelope. So because of these random phase jumps here, right? You can see that it has actually a lot more frequency content than just the envelope, right? So that's where the spectrum comes out to be much bigger than 1 over the pulse width. Okay, so basically the point is for these kind of incoherent sources, the pulse width really doesn't matter. So what is the duration of these pulses, what data rate you are operating at, that really is immaterial. The bandwidth, the frequency content of the optical signal just depends on my source, because these phase fluctuations are what determining the spectrum. Okay, on the other hand, if you go to coherent sources, like single frequency lasers, which are basically what are mostly used nowadays in modern day telecommunication systems, right? So these sources will be like a laser at a very precise frequency. They're stabilized lasers that oscillate in a single mode and give out a single frequency omega naught. Okay, so there are no phase fluctuations. Okay, so in that case, you can see that. So now, basically, the pulse looks like this, right? So basically, you have a smooth envelope which is just multiplied by a particular carrier frequency, right? So again, you know from your basic Fourier transforms that if you have some signal which you multiply by a carrier in the spectral domain, what that means is that you shift the spectrum to the carrier frequency, right? So basically, what you'll get is the Fourier transform of A of t, but centered at omega naught. Okay, and again the Fourier transform of A of t will just be inverse of the temporal derivative, because that's a real thing. Okay, so for these, the spectral bandwidth is sort of determined by the pulse width. Okay, and the source, because now it's like a single frequency source, the line width of the source is very, very narrow, and that does not come into the picture. The bandwidth, spectral bandwidth, is decided by the pulse width, right? But in any case, so of course this is much worse, right? Here the bandwidth would be, so for example, for LEDs, typically the bandwidth in frequency would be a few terahertz, right? Or in wavelength units that, so let's say if you're working at 1.5 micron, that would be like 50 nanometers bandwidth. Whereas for single frequency lasers, the line width is extremely narrow, right? So the source line width is like, let's say, less than a megahertz. Okay, so that for all practical cases for the data rates we are operating at this the frequency scale we are looking at, that's basically 0. Okay. And so again the pulse widths that we are using are typically, let's say, tens of picoseconds. So then the spectral width here you can see would be tens of gigahertz. Okay. So in this case, the spectral width you get is 2-3 orders of magnitude lower than this case. Okay, and again you can imagine that. So now, if your dispersion is determined by different frequencies traveling at different group velocities, then this case would be much worse, right? Because you have a much broader spread of frequencies, right? So a lot of different frequency components traveling at different speeds, so the pulse spreading will be much worse here. Okay, and we'll see basically the pulse spreading depends on just the bandwidth, right? Because again it's coming from different frequency components traveling at different speeds. Okay. Yeah. So how do we calculate the pulse broadening in this chromatic dispersion case? Right. So in the intermodal case, we just took different modes. We could even treat them in the ray picture, right? So either if we do it in the wave picture, you calculate sort of the propagation constant for different modes, and then you calculate basically the group velocity at different modes. Or in the ray picture, you can just calculate the time taken by different rays. That's what we use, right? So in this case, right? So basically, we want to see this thing, some pulse here broadens by an amount. So we send some tau naught, and so here the pulse width becomes tau naught plus some delta t broadening. Okay, so there's some fiber of length L. So if we take one particular frequency component here, right, out of this spread of frequency, let's just take some particular frequency omega. So the time taken for that frequency component to traverse the length of the fiber is length divided by group velocity at that frequency. Right? So you can think of the power being distributed across these frequencies, right? So you have photons at different frequencies. So the time that a photon at frequency omega takes to go across the fiber is the length divided by the group velocity at that frequency. Right? And we know that this by definition is the derivative of the propagation constant. So dg is d omega by d beta. So 1 over dg is d beta. Right. So for example, for SMF, this would be the propagation constant for the LP01 mode at frequency omega, right, or wavelength class. So now the broadening delta tau we can write as the dependence of tau on omega times the bandwidth, right? So we are saying that the transit time just depends on the frequency, right? So the spread in the transit times would be sort of the derivative of the transit time with respect to frequency multiplied by the spreading frequency. And so when we take the derivative here, we'll see we'll get a second derivative of the propagation constant. So the temporal broadening here, delta tau, by how much the pulse spreads, you can see depends on the length, of course, right? The longer length you propagate, the more the pulse will broaden, of course. Depends on bandwidth, again, the wider bandwidth you have, more the broadening. And then it depends on the second derivative of the propagation constant with frequency, which is known as beta 2. Right? So in general, the nth derivative of beta with respect to omega would be denoted as beta sub n. Right? So that in general is known as nth order dispersion. But here, so you can see our concern is with the second order. Okay, so that's denoted as beta 2, and it's known as GVD. Okay, group velocity dispersion. Right. So what is this? So right, d beta by d omega is, so this is the derivative with respect to frequency of 1 over Vg. Right, so this is basically capturing how the group velocity changes with frequency. So that's why it's called group velocity dispersion. Okay, so you can see that, so I can just define beta 2 as the broadening over some length of fiber divided by the bandwidth of the source, right? So you can see the units here, so this is seconds, this is meter, and this is per second. So this is second square per meter. Okay. You can also check from here. Right. So typically, for fibers, this is denoted in picosecond square per kilometer, because in those units, they come out to be some actual numbers instead of like carrying some 10 to the minus 23. So they're denoted in picosecond square per kilometer. Okay, so basically, this beta 2 is the broadening that you get per unit length, per unit bandwidth of the source. Right, so here we are measuring the broadening in picosecond, the length in kilometers, and the bandwidth in per picosecond instead of per. Okay, so equivalently we can compute this in wavelength units, just like the spectrum, for example. Right, so I can equivalently write the broadening as the derivative of the transit time with respect to wavelength, and then multiplied by the bandwidth in wavelength length. Okay, so again, so we write the transit time at wavelength lambda as the length divided by the group velocity at lambda. So if we write that as C over Ng, right? So here this Ng is the group index at wavelength lambda. Right, so we just plug. If we plug this expression here, so we get dng by d lambda. So we get L over C here, the derivative of group index with respect to lambda times the vector. Okay, and now recall that the group index in terms of the phase index, like the usual refractive index, can be written like this. Right? This how you get this. You should know this from your basic optics course. Right, so there is an expression in terms of omega also, for example. In terms, so Ng as a function of omega is n plus omega times dn by d omega. As a function of wavelength, it can be written like this, where n is the usual refractive index, so phase index. Right? So now d Ng by d lambda, you can see, so the first term will just get the derivative of Ng lambda. Right? And the second term we have to use the product rule, right? So we get two terms. Right, so the first term cancels out here, you can see, and we are left with the second derivative of the refractive index with respect to wavelength. So again, now, so the broadening I can write as some length times this quantity here. So I take C, so the C goes in with this, times the bandwidth. Okay, so now this looks similar to here, right? So we had length, bandwidth, and then some other quantity. So in wavelength units also again we have length, bandwidth, and some quantity here. So just like the GVD we defined here, this is known as the dispersion parameter. This is denoted by capital D. It's known as the dispersion parameter. Right, it's basically the same thing, right? We are writing the same thing just in sort of different units here. Right? So physically, both of these are talking about the same thing, right? GVD and dispersion parameter, they're talking about the same thing, but it's just looking at it in different units. Right. So what are the units of this? So you can see D is the broadening per unit length per unit bandwidth in wavelength. So here I get second, then length, and then another length, because delta lambda is also wavelength units is length. So I get so I have second and then 2 meter units here. So again, just like this guy, this is usually denoted in picosecond per nanometer per kilometer. Right? So usually the broadening is measured in picosecond per kilometer of fiber per nanometer of a bandwidth. Okay. So the units for D are picosecond per nanometer per kilometer. Right, so you can see, of course, the D and beta 2 are related, right? They're talking about the same thing and we're just doing a change of units. So you can check for yourself that beta 2 is related to D like this. Okay. So it's just some constant of proportionality which depends on the wavelength you're operating at. But one important point is that there's a negative sign here, which means the sign of beta 2 and D is opposite. Okay. So yeah, that's one thing, important thing to keep in mind. Then some more terminology here. So again, so now each of these quantities can be positive or negative, right? Because so beta 2 is the second derivative of beta with respect to omega, right? So you can imagine for at any given wavelength in some material, this could be positive or negative, right? Similarly here, this is the second derivative of the refractive index with respect to wavelength. So depending on the wavelength of operation in some particular material, this could also be positive or negative. But when one is positive, the other is negative because they are related like this, right? So these two regimes are denoted by two, I guess, two terminologies, right? So the term normal dispersion okay. Sometimes you would see the term positive dispersion also, but that is more confusing, right? because you don't know which you are. By positive, you mean this is positive or this is positive, right? So, but you will see in some places this terminology being used. But as I said, that can get confusing. A more useful terminology is to use the term normal dispersion. Why is it normal? Because for most materials in most wavelength ranges, this is the sign of the dispersion. So beta 2 is positive, or the D is negative. So this positive refers to the beta 2 being positive. Okay, but yeah. So normal dispersion we'll just refer to as a normal, and the other one is known as anomalous instead of positive and negative, because this way you avoid any confusion. Right, this is the opposite case. Okay, normal and anomalous. So this is called anomalous because typically this is quite rare, right? So if you take any material and try to calculate, so for example, the refractor index is a function of wavelength, right? In any material, now you shall try to calculate beta 2. Most of the time, for most materials in most wavelength ranges, you will get beta 2 to be positive or D to be negative. So that's why it's called normal. And in rare cases, you'll get anomalous. But actually, it turns out for fibers, right, made out of silica glass, at the telecom range of wavelengths, right? So from roughly 1.3 to 1.6 microns in that range. Okay. Turns out by accident, I guess, that the dispersion is actually anomalous. Okay. So the rare case actually turns out to be the usual case for silica fibers. Okay. And that is also, what can I say, is a nice coincidence that nature gave that has been very useful in sort of, again, building this global connectivity with fiber optic networks, because we can use that to sort of really eliminate this pulse broadening and dispersion to very large extent, and we can go to extremely long distances. Okay. So, yeah. Anyway, we'll see more details about that. Okay, so what is the difference between these two physically, right? What happens is that in both cases you get broadening, right? It's not that. So this is, what should I say? So this is the magnitude, right? Similarly, right? So in both cases, if it's positive or negative, you will get broadening. It's not that in one case you'll get broadening and in the other case you'll get compression. Okay. In both cases you'll get broadening. Okay, so another way to think about that is, so let's say if I'm starting with some pulse here, right, that has some, so let's say imagine this pulse like with some envelope and some carrier frequency. So when we find the spectrum here, right, so all these frequencies in the spectrum are sort of launched at the same time. Okay, that is known as a transform limited pulse. Okay, and that is sort of the minimum pulse width you can have for a given frequency spectrum. Okay, and then as this pulse propagates through the fiber, what is happening? These different frequency components are traveling at different speeds, right? So basically, at the receiver, different frequencies come at different points in time, right? So you can immediately imagine what that looks like, right? So the instantaneous frequency in the pulse is basically what is the frequency at which this carrier is oscillating, right? So now this carrier will oscillate at different frequencies within the pulse at different time, because now the frequencies have spread apart in time. Okay? So consider this case, for example. So beta 2 greater than 0. So recall beta 2 was the derivative with respect to frequency of 1 over the group velocity. So if this is positive, this means that 1 over Vg increases with increasing frequency, which means Vg decreases with increasing frequency, right? Which means what? Higher frequencies travel slower, right? Or lower frequencies travel faster. So lower frequencies are denoted by red, and higher frequencies are denoted blue, right? For example, in the visible spectrum, right? Red is towards low frequencies and blue is towards high frequencies. So the low frequencies travel faster, right? And the high frequencies travel slower. Which means what now at the receiver, so now if I am measuring the pulse with respect to time, so I receive the lower frequencies, the red frequencies first. Okay, so here you can see I'm exaggerating this a lot, right? Of course, for the scales we are looking at, you'll have many oscillations here, right? But I'm just exaggerating this to show the effect. And then as you go towards longer times, the higher frequencies arrive later. Okay, so this frequency now starts going up. So the pulse now at the receiver end looks like that. Okay, so the instantaneous frequency here now is a function of time. Okay, so that shows up, you can see, for example, that will show up in the phase of the pulse. So this is known as a chirp. This time-dependent instantaneous frequency is known as a chirp. Right? It's coming from, so if you've heard birds chirping, right, it sounds like as if it goes from low frequency to high frequency, right? Something like that. So if you, for example, if you record a bird's chirp and take if you record the waveform, it will look like this. Okay, so it's called a chirp. And the only difference between these two is basically the sign of the chirp is opposite, right? So now, this is the case for normal dispersion. If you have anomalous dispersion, basically this situation is reversed, right? So now, so in this case, red travels slower, right, and blue travels faster. So the pulse still broadens, but just the chirp is now opposite. Right? So now it looks like that. Okay, so sometimes this is known as positive chirp. Basically, omega t increases with t. Right? So if I plot omega t versus t, that's an increasing function here. Whereas in this case, omega t versus t is a decreasing function. Okay, so this would be called a negative chirp. So just the sign of the chirp is different in two cases, but in both cases you get broadening, right? Which depends only on the magnitude. So that's the difference between this normal and anomalous. Okay, so recall we had divided this chromatic dispersion or intramolar dispersion into two basic physical causes. One was material dispersion and the other is waveguide dispersion. So we'll discuss each of them in some more details. Right. So another thing to note is that the frequency spectrum, right? So the pulse broadened and it chirped, right? But so this is in time. If you look at the frequency spectrum, right? So that will remain unchanged, or like the magnitude or the power spectral density will remain unchanged. There will be no change in that. Right? Because right, all this is a linear effect. There is no, we are not talking about any losses here, like frequency dependent loss, or we're not talking about any nonlinear process which can mix different frequencies. Okay, so this is just a linear phenomenon, and there is no power. The total power in the pulse remains the same. Okay, and also basically, yeah, the frequency, the power spectral density remains the same. Okay, so how is this possible? You can think about that a bit for yourselves. Right, the clue is that the power spectral density remains the same. So the mod of E omega or mod square remains the same. Okay, but if you look at E omega, as I said, that's a complex number. Okay, so that will not remain the same. And yeah, so the only way that can happen is if you have a phase factor, right? So what happens is that, so if you have some E0 of omega here, after length of propagation, basically the frequency components get multiplied by some phase factor, right? So that the mod remains. But this phase is now frequency dependent, which is what is leading to this chirp. Right. So if you look at material dispersion, right, that is again basically just coming from, so here you see this is a derivative, second derivative of the refractive index with respect to wavelength, right? So for example, if you look at silica, so which is what optical fibers are made out of. So we can first plot the refractive index as a function of wavelength. Okay, so we plot the near infrared range, which is what is important for example, optical communications. Specifically, optical communications, modern day systems use these range of wavelengths, as I said, 1.3 to 1.6. So for basically all materials, as you increase wavelength, the refractive index goes down. Okay, this is true for any material and also for silicon. Okay, so but the scale of the change you can see here. So this goes from 1.444 to here it's 1.456. Okay, so the change is happening like in the third decimal place or something. It's very small. Right, so over this entire range of wavelengths from 0.8 to 1.6 microns, it's only changing by 0.01. Okay, so you might think that's a very, very small change that does not matter, but we'll see it's quite the contrary. Okay, so this is for 100% pure silica. So for optical fibers, we sometimes also dope the glass with some other atoms to change the refractive index. Okay, so for example, we need some index difference between the core and cladding. Right? So for example, we dope the core region with some material to increase the refractive index slightly. So that will change this by very, very small amount, right? Again, the deltas we were talking about was 10 to the minus 3, 10 to the minus 2, remember. Anyway, so for pure silica, it looks like that. So now, basically, the relevant quantity here is the second derivative, right, of this curve. So let's first look at the first derivative. So it's a monotonically decreasing function, so the first derivative is always negative, right? dn by d lambda is negative. So this is in per micron. Okay, so what happens is there's an inflection point around 1.3 microns here. So it's always negative, so see, these are negative numbers. But the slope is sort of going towards 0 until this point. Okay, and then it increases again. Okay, so this is precisely a wavelength of 1.27 micron for pure silica. Okay, so you can now see the slope of this will be the second derivative, right? So here you can see that here the slope is like the magnitude of the slope is decreasing, but because it's negative, this slope is increasing. So d square n by is positive here, right? Which means what? So d is minus lambda by c multiplied by the second derivative. So d is negative here, right? And then after this point, d becomes positive because this sign changes. Okay, so now I've got d, the dispersion parameter. So we put a subscript n to denote its material dispersion. Again, so units are picosecond per nanometer per kilometer. Okay, so it will cross, d will cross 0. At this wavelength, right? And it's negative here. So it looks something like this. Okay, so you can see for the telecom range of wavelengths, right? So telecom range is here. The dispersion is anomalous, so d is positive. That's anomalous dispersion. Okay. And not only is it anomalous, like it's crossing 0 right around 1.3 micron, right? So the dispersion is also very small, right? So for example, if you look at like, for example, 0.8 micron, the dispersion is quite large. So for example, the first generation optical communication systems, which were first demonstrated around like 1960s or 70s, there the wavelength of operation was around 800, 850 nanometer, right? And they were severely limited by dispersion, right? So, right. So now you can see, for example, if you move to 1.3 micron, you're basically almost zero dispersion, right? So, which you might at first hand think that's great, right? That means that there is no pulse product. So of course that's not true, right? So recall here that, so we just took the first derivative and multiplied by this, right? We can also take the higher order terms. second derivative multiplied by delta lambda square. Right? So if this is 0, so at 1.3 microns, let's say this is 0, then this next higher order term. So that will be third order dispersion, the third derivative of refractive index with wavelength that will now determine the broadening. Anyway, and so modern communication systems, as you know, the main wavelength of operation is around 1.55 micron because that's where the loss is minimum, as we had discussed in the first few classes, right? So at 1.55 micron here, you can see that the dispersion is about like 15 to 20 picosecond per nanometer per kilometer in a bare silica fiber. Okay, so there are various techniques to compensate this dispersion and bring it near zero, so that you can also get the lowest loss and the lowest dispersion at the same time. But if you just take the bare silica fiber, the dispersion at 1.55 is worse than 1.3, but the loss is opposite. Loss is worse at 1.3 compared to 1.5. Right, so for example here again, so at let's say lambda 1.55 micron, the most popular telecom wavelength, the material dispersion is about 20 picosecond per nanometer per kilometer, right? So in this entire range, the dispersion is anomalous. So again, if you compute the broadening here, so for example, if you take an LED source, okay, as I said, the spectral bandwidth typically would be, let's say, 50 nanometers at a wavelength of 1.55 micron. So you can compute from here the broadening per unit length would come out to be about 1 nanosecond per kilometer. Right? So I just multiplied D by the spectral bandwidth. So this would be just D times delta. Right, so this you can see, so for example, if your link is 1 kilometer long, then your data rate is limited to less than 1 gigabit per second, right? Pulse width, because the pulse is broadened to a nanosecond already by the time it gets to receiver, so you cannot have more than 1 pulse per nanosecond, which means your data rate has to be less than 1 gigahertz, right? And if you increase the distance further, then your broadening goes up further, your data rate falls further, right? So you can see this is severely limiting, right? So LEDs were used in the initial days for short links and for initial demonstrations, but as I said, you can see nowadays they are not practical at all, right? On the other hand, if you go to so there are these laser diodes, okay, which are somewhere intermediate between like a pure single frequency laser and LEDs. Okay, so they have spectral bandwidth, let's say about 2 to 5 nanometer. So if you take 2 nanometer here, then now you can see that the broadening goes down to about 40 picosecond per kilometer. Okay, one thing to note here is these values are much smaller than the intermodal dispersion values that we had. Remember, right? So for step index, we had values like, I don't know, 20 nanosecond per kilometer or 50 nanosecond per kilometer or something. Okay, and then for graded index fibers, we were able to get it down to maybe like hundreds of picosecond per kilometer, right? So these are already lower than that. Okay, but for modern day communication systems, these are still too large, right? For really long links of hundreds of kilometers and data rates of tens of gigahertz, this is still too large. So we go to single frequency lasers where basically the source bandwidth is, you can assume to be 0 here, right? And then as we discussed, the bandwidth would just be the inverse of the pulse width. So we'll discuss a little bit more about when we go to single frequency lasers, how do we describe the broadening? We'll discuss in the next class. Chirping always leads to temporal broadening. So if you start with an unchirped pulse, right, then it will always lead to broadening, right? And for incoherent sources, yeah. What you can do is, since the chirping is, as we saw, could either be positive or negative, right? If you start out with an already chirped pulse, right, then you can try to eliminate the chirping, right, by adding the chirp of the opposite sign, right? So, for example, let's say we start with an unchirped pulse. Let's say we go through normal dispersion. So we get a positive chirp here, right? And the pulse will broaden, right? Because we are starting with an unchirped pulse, so all the frequencies you can. So this means that all the frequencies are present together. Okay, so it's something like if I plot with time where all the frequency components are, like so the spectrum has some extent from omega 1 to omega 2. All these omega 1, all the frequencies in between to omega 2, all of them are present together at the same time, which means there is no phase difference between these different frequencies, right? Actually, these would be sine waves, right? Because they are monochromatic. Right, so how we get this pulse is by adding all these sine waves of different frequencies without any phase shift, right? They're all together. So that's an unchirped pulse. And now what happens when they travel through the fiber is because they travel at different speeds, they sort of have now a lag with respect to each other, or equality of phase difference, right? That's what this frequency dependent phase I was talking about, right? Which leads to this product. So now, but now imagine, so now I have a positively chirped pulse, and now I send it through a fiber which has anomalous dispersion. Right, so now what would happen? So here the red frequencies, the low frequencies are in the front of the pulse, and the high frequencies are towards the back. And now through the anomalous dispersion, the higher frequencies will travel faster than the lower. Right, so this will catch up. So, for example, if you design the lengths to be such and this GBD coefficients to be of the right value, then basically at some point you will get here back this pulse, right? Because now red and blue will again catch up together. If you propagate further in the same fiber, then now blue will overtake red, and now it will broaden again. Right? So if you start with a chirp pulse, you can actually compress it. If you send it through a fiber which has the opposite, which introduces the opposite chirp to your starting chirp. And again, that's fundamentally because a chirp pulse has a longer temporal duration than what is known as a transform limited pulse, the minimum duration that a pulse can have for a given spectrum. Right? The spectrum, as we said, is not changing except for phase. Right? So to keep the spectrum the same, the only way the temporal extent can change is by chirping. So anyway, I hope that's clear. So you can imagine, so this is a technique for dispersion compensation in very long optical communication links, right? So one way to compensate for the dispersion broadening is you introduce another fiber with the opposite sign of dispersion. Okay. So we'll take a look how we can do that, like how you can tailor the dispersion, right? So what we saw today was just the material dispersion of glass. So that would be true for any fiber, right? The same for any fiber if it's made out of the same glass material. But so we can change things a little bit by two things. One is, as I said, doping with different atoms to change the refractive index and hence the dispersion profile slightly. And the second technique is to use waveguide dispersion, right, which we'll discuss. So waveguide dispersion we can tweak by, for example, having some graded index profile or changing the pore size or the pore cladding index difference. So we can actually have fibers with different kinds of dispersion profiles.